Hi everyone. For the next couple of videos, I'll be traveling, so I'm not going to be at home or in my office. They won't be as organized and they won't be as polished as my previous videos. What? Those previous videos were polished? So the thing is, whatever pops into my head are going to be the major concepts, the most important concepts, so which is good for you. I won't put the smaller details or the subtleties or too many subtleties about each reaction. The things that I'm leaving out from Unit 5 that I normally teach are not really much of a focus in Organic 2, if you choose to take that, or the MCATs, if you are headed in that direction. Okay. For Unit 5, we are going to rattle off that list of reactions, and for each of those reactions, or for most of those reactions, we're going to talk about the mechanism and any properties or any things that result in a certain type of product. Sometimes we're going to focus on, does this reaction give a major product? Or sometimes we're going to focus on, does this reaction give products that are isomers, enantiomers or diastereomers? Our first reaction, I think this was on Wednesday, was reaction 5A, and I didn't give you the name of that reaction, but here I am going to give you the name because this is how most people keep things straight in their head. Okay. Sometimes I will ask in an exam, look at the following chemical equation, tell me what kind of reaction it is. Okay. Thankfully, most of these reactions are named rationally. The first one is hydrohalogenation, and you are adding a hydrogen atom and a halogen atom. The halogens are in order fluorine, chlorine, bromine, iodine, going down the group 7. So I have the designation. Okay. This is good to know because if you need to refer to it, like you're taking your doing your practice problems, you can say, well, Jose, I was having trouble with anti-Markovnikov hydration. And Jose could say, well, okay, let's take a look at your notes, which is reaction 5E, and then you can find that fairly easily. You don't want to spend a lot of time searching for that piece of information that you know I said, but it's just on the tip of your tongue and you can't quite remember it. That's why I give these categories, these notations. You should also know your name because, again, this is a very good clue about what's going to be added to your alkene. Oh, by the way, if this looks familiar, yes, because this was on a video in Unit 3. I think it was, it's hard to remember now, but in Unit 3 videos, one of the 6 that I put up, I talked about our first organic reaction. It was this one, hydrohalogenation. Alright, enough about that. I like to put the reagent above or below the arrow. Okay, in this case, I'm going to have hydrochloric acid, and I'm going to add an atom to that carbon and an atom to that carbon. And the 2 atoms I'm adding are hydrogen and chlorine. And the thing is, how should I say this? I picked a medium challenge example because in this case I do want you to understand that there might be stereoisomers, and I'll explain this in just a bit. But in this case, the stereoisomers are chlorine wedge and chlorine dash. A rule that I almost always stick to and expect my students to stick to is if you draw wedges and dashes, it has to be off of a chiral center. You really shouldn't draw dashes and wedges off of carbons that are not chiral centers. So, if no chiral centers, under rare circumstances, you should never draw wedges and dashes. So don't draw wedge dash. Okay. Now, this is a type of reaction, and it's called addition reaction, but to be more specific, electrophilic. And I did explain what nucleophiles and electrophiles in that video where I went over hydrohalogenation. Okay. Actually, while we have time, well, we don't have a lot of time, but let me show you on Moodle where this video is. If you're already feeling a little bit unsteady about the reactions, which is understandable, review this video that from Unit 3 that we're going to locate. Actually, why am I doing that? Let's go to YouTube. Wi-Fi. I think this is a channel. I hope it's a channel. Yeah. Do you see this? Unit 3 hydrohalogenation. I went in detail over this reaction, so I'm not going to go in detail for this first reaction, reaction 5A, because I already had talked about it in Unit 3, the fourth video in Unit 3. Why electrophilic addition? Because you're adding an electrophile. Your electrophile is the species that's electron poor. And remember how I said that this is a nucleophile because pi bonds are electron rich. Electron rich attacks electron poor. We're adding stuff to these carbons, so we're adding the electrophile. In most cases, you're actually adding a nucleophile. So I know it depends on which perspective you're looking at, but if I take the main organic starting material, the one with the carbons, I'm adding an electrophile to that. Now, I'll go over the mechanism. I was going to skip that, but let me just review that. We have a double bond plus HCl. These mechanisms, if you speak language, or if you learn the language, or you play a sport, or you play a musical instrument, you do understand that to be good at it, or even to be slightly competent at it, you have to repeat exercises over and over again. This is an exercise. If you think you're going to understand this by just looking at how I do it, that's almost like learning how to drive a car by just watching a person drive a car. And if you think you could get away with just doing this only once without your notes, yeah, good luck. Giving a piano recital, or taking a penalty shot in extra time in the soccer game without putting in that repetitive practice. Okay. So I'm going to put the carbocation on the secondary carbon, and I explained that already when we talked about carbocation stability. We produced a chloride ion, and I am going to draw the lone pairs. And I'm going to draw our last arrow. This is where the electrophile. Oh no. This is the electrophile. So it is based off of the first step. This is actually a nucleophile, right? Electron rich, the attacker. And there are a couple things I want to say about a mechanism. The first thing is, you notice that I didn't put a wedge or dash in here. So for mechanisms, no wedges or dashes. You don't have to, and I wouldn't. Now, this is 2 enantiomers. Now, why did that happen? Because this carbocation is flat. We know that this carbon is sp2 hybridized, and those are trigonoplanar. So imagine these 4 carbons, or maybe just these 3 carbons, right? Three points make a plane, and that plane is like this. Side view. The chlorine can come from the top or the bottom. Top or bottom. So either up or either down. But then when you look at it from the face, what is that? Up and down now becomes in and out, wedge and dash. So this is a 50-50 proposition where it could come from either side. Actually, the way it's written on the paper, yeah, the chlorine can come from the front, or the chlorine can come from the back. So the chlorine, and it's 50-50, it's just probability. That's 50-50 front and back. But the idea is, those 2 situations will give you a different outcome because this is a chiral carbon. Do you notice that if this methyl group was not here, front and back would give you the same molecule, right? They are identical. And that's easy to know because that carbon's not chiral, so we don't have R and S. But when we have an ethyl group, we do have R and S. Half of them are R, half of them are S. This will be called racemic. So there are 2 ways that I could ask you to draw the product on an exam for this particular case. Let's switch it up to HBr. Either you could say I want to make sure I do this right. Yeah. If I'm asking for stereochemistry, you could put that, and I could ask you, or I could let you go ahead and write enantiomer. You don't have to draw the dash version. Okay. I still want you to know, though, that this is racemic. Racemic, again, is a mixture of 50-50 mixture of 2 enantiomers. They have to be enantiomers. 50-50. If I gave you this molecule, though, I gotta make sure that it's gonna give me no chiral carbons. Oh yeah, this one. How about that? Let's do HI. Okay. Go ahead and write the product without stereochemistry. Okay. And I'll show you why in just a bit. But draw the product. Pause your video. Okay. So without stereochemistry, without wedges and dashes, you have this. You notice that this is not a chiral carbon, so you're done. That's your final product. But if I had shown you this, oh, how about this? I'm trying to predict whether this would be chiral or not. Let me give you a little complicated, but let me give you. Oh yeah, let me give you that. Okay, let's do HI again. Without stereochemistry, you have this molecule. Okay, it's a little bit more complicated, but what you need to recognize, or else you are going to miss points for not understanding that there's a mixture. Here there's no mixture, no RNS. You're done. But for this one, a great strategy is to draw the product without stereochemistry and realize that, oh, I have a chiral carbon. And that chiral carbon, now that I could come in from the front and back. So this is an answer. Sometimes I ask on a question, draw the answer without any stereochemistry. And for this this example, this is fine without stoichiometry. But if I ask you with stereo, okay, I would say with stereo when appropriate. So again, if I say with stereo, don't be tempted to draw any wedges and dashes here because it's achiral. Because, see, this carbon has 2 alpha groups. It doesn't have 4 different groups. So what do I do, or what do you do if I ask you with stereo when appropriate? You're going to realize that you have a chiral carbon and you are going to give me wedges and dashes or some indication that there is stoichiometry. Now again, you could draw both enantiomers, or you could put the word plus enantiomer, but you should always write with CMYC. So I'm just gonna draw the other enantiomer for CMYC. Those of you who were not really catching the important parts in that Unit 3 video when I first described hydrohalogenation, rewatch this video. This one here, the 4th video. Okay? Because what am I not talking about? I'm not talking about a very famous scientist. Remember whose name that was? I've talked about Markovnikov already, so I'm not going to dwell on that here, but what does Markovnikov tell you? Markovnikov tells you that the major product, comes from the more stable carbocation. So when you look at this situation, you want the H on the N carbon and the carbocation on the more substituted carbon. For this situation, you want the carbocation on the more substituted carbon. And same thing for here. Okay. Markovnikov said that. Before we go on to the next reaction, some people understand Markovnikov's rule as the rich get richer. The rich get richer. And the money is hydrogen. So if this carbon has 2 hydrogens and this carbon has 1 hydrogen, the rich get more hydrogen and the poor get the leftover. Oh, did I mess that up? This should be... I'm going to change this back to chlorine. The rich get richer. This carbon has 1 hydrogen. This carbon has 0. The rich get richer. And iodine here. You notice that I'm only looking at the carbons that are part of the double bond. That is hydrohalogenation. I will implore you to do your Unit 5 practice with your notes and with the textbook at first. If you have questions at that point, ask me those questions. I don't think it's... I mean, I'll still try to answer. My time's limited, but I'll still try to answer your questions after you watch the videos. But why don't you see how to apply these notes? Okay, you'll have the notes. Apply these to your problems, and then if you have a question, let me know. I think it's not... You don't know what you don't know until you do the practice problems. So this is reaction 5B. Reaction 5B we're going to call acid catalyzed hydration. It's going to have a very similar mechanism as hydrohalogenation, and it's going to have the same type of concerns that we're going to have, whether the carbon, whether we have to worry about Markovnikov's rule, and whether the atoms that are added do we have to worry about wedges and dashes. Let me use our same alkene. In this case, our reagents are going to be water and acid. You have to be flexible with organic chemistry, because maybe I don't have H3O plus, maybe I have acetic acid, or maybe I have hydrochloric acid. I wouldn't use hydrochloric acid actually. Maybe I have sulfuric acid. Most likely it's going to be sulfuric acid. But you know that when you add a strong acid with water, there's going to be a proton exchange very quickly, and you have mostly H3O plus and not the actual original acid. The product here is, if you want, you can still draw your two arrows to remind yourself both carbons get something. And we have this molecule there. Now, those of you who are eagle-eyed, what do you know about this molecule? This molecule has a chiral carbon. We created a chiral carbon. So when I say that it has a chiral carbon, I also have to say that we created it. It doesn't matter if there was a chiral carbon before. It's what matters is, do we make one or not? Because now we have to consider where that OH is. Now the thing is, this is without stereochemistry. Without stereochemistry. And I'm going to here put a little note, with stereo, you have a racemic mixture. And it's racemic. We know that because, you know, if I was trying to answer this question, draw the products with stereochemistry when appropriate, honestly, I would, on a scratch sheet of paper, I would draw this first. I got to get at least the connections correct, and then I'll analyze and say, I made a chiral carbon. Then let me go back to the exam and draw these two. Okay, scratch paper. Actual answer. For the exam that I'm planning to give you, I'm gonna make everything. Use stereochemistry when appropriate. When appropriate. If it's not appropriate, don't draw any wedges and dashes, just like for this example here. Do you see how you have to be now? You can't forget your exam 1 stuff. You can't forget what's an enantiomer, what's a diastereomer, what's RNS. We taught those early because reactions are applying those concepts. There's no way that you can deconstruct or disconnect these major important concepts. Now again, if I got rid of this methyl group, then the product would be like that, and there's no chiral carbon, and you should never draw wedges and dashes, even if I ask you for stereochemistry. Because there would be no stereochemistry. Mechanism. Oh, before we do mechanism, take a look at this. It's about 3 inches high. Okay. This almost matches the dimensions of a note card. So I'm going to try to add as much information, useful information as possible on this note card. The first thing is that this reaction is following what's called Markov-Nikolsky rule.
I'm going to the hospital.
Okay. Just a second. Okay, Markov-Nikolsky rule. Yeah, I don't know if you heard that. My dad's going to the hospital. He's picking up it's cool. My mom got an MRI, and they're putting all the data on a well, maybe it's not so cool because they put it on the CD. They're not giving her other doctors a electronic version, I guess, over email or a private server. 2020, guys. Markov-Nikolsky rule, and let's see what else. Oh, not stereo selective or non-stereo selective. I'll use non-stereoselective. So what does that mean? Non-stereoselective with an E. Markovnikov's rule tells you that you are picking between two or more constitutional isomers. Okay, so it prefers a certain constitutional isomer, because the other molecule that's possible is, what if I put the OH on the N carbon? Okay, so I'm not going to draw it, but visualize, what if the OH was here? Then I have to choose between two constitutional isomers. Okay, and I chose this one, the one that follows Markovnikov's rule. I say it's non-stereoselective because both of these are made 50-50. Do you see how it's not selecting either the R or the S? Which one's a R? This one's a R. Okay, do you guys see that? R, S. With a little practice, you could be as fast. Probably you're already faster than I am. 1, 2, 3, and H is away from us. R. It would be stereoselective if we ran this reaction and we only got exclusively R or exclusively S, because we're choosing one over the other. It's a little bit of semantics, but yeah, the minor product is the OH on this N carbon. Some professors want you to draw that. I don't. Okay, draw the major organic product, and for this, these two are 50-50. The mechanism is going to be pretty similar, because again we're going to have the pi bond attack an electrophilic hydrogen, but in this case, instead of HCl, you have H3O+. Okay. Draw the arrow from the middle of the pi bond, either from the top or the bottom, it doesn't matter, but draw it from the middle. See, this is where students get a little bit, they overthink things, and they say, well, let me demonstrate that this is Markovnikov by drawing the arrow from this carbon to this hydrogen to prove that I know that the hydrogen goes here. But remember our mantra, mechanism arrows start from a source of electrons. An atom is not a source of electrons. The electrons are either going to be a bond or a lone pair. So in this case, we start from a bond. Well, both cases, we start from a bond. And we have to break this bond because hydrogen cannot have more than one bond. The hydrogen goes on the end. The carbon second from the end is naked. It has 3 bonds, and there's where your plus charge. And we did produce water. And I know it's strange to draw it like this, but that's perfectly fine in terms of a condensed structure. There's only one way that this could work, where we have oxygen in the middle and hydrogens flanking the oxygen. The nucleophile attacks the electrophile. I don't know if you could hear that. There's something rattling in my laptop, like a loose piece of plastic. And if you run out of space, you're perfectly allowed to curve it down. Okay. With a mechanism, some professors and textbooks draw each step line by line. Okay. I like to do a snake. Okay. So instead of redrawing this here and do the next step, step 2, I'm going to draw step 2 here, and I have this. Just following my pink arrows. Okay. Oh, by the way, here's another rule that most 95% of the professors follow. If you draw a lone pair on an atom, because you are using it to draw a mechanism arrow, you have to draw all the lone pairs on that atom. So if draw a lone pair on atom, see, I wanted to draw this lone pair specifically because I'm going to move it, or I'm going to use it to make a bond to this carbon. See, the lone pair is now here. But if I draw that one lone pair, I have to draw all on that atom. You can't once you start filling in things, you can't stop short. Or you could not draw them at all. Like, I don't know, for here, I didn't draw the lone pairs, it's just product. I'm not using any of the lone pairs to draw a mechanism. So you have to draw all on that atom. This video is going to be way longer than 30 minutes, and it's only going to be the first of several. Alright. If you need a break, go ahead and take a break, water break, or pause and pause it. Do you notice that we're not done? That's not my product. Okay. It's very tempting to draw your product with just one hydrogen, because that is your product, but it's not the product of the step. Because in this pink arrow, I'm not saying we're doing anything with any of the oxygen-hydrogen bonds. So you're bringing in everything, both hydrogens like this. You have to get rid of one of those hydrogens. We are in a sea of water, okay? You're not worried, typically, with an organic reaction about stoichiometry, at least in the lecture. Now, in the lab, you are worried about it, okay? You are worried about it because you need to do calculations to figure out percent yield and theoretical yield. But, again, here, we're not worried about putting coefficients. Okay, that would just be complete, not waste of time, but it's so unnecessary, right? It's already good enough to be able to predict the product and show it in stereochemistry. So here's the mechanism. I'm going to pick up another water molecule, okay, from the solvent, and just strip off that hydrogen. Remember, I'm allowing you, and I'm suggesting that you draw no wedges and dashes with a mechanism. When you see this mechanism, what do we know about it? We know that it's 3 steps. Okay. This is new information. I haven't yet talked about the number of steps, and we're going to talk about a little bit about the energy diagram. We have 3 steps. You count it like this: 1, 2, 3. That's different than hydrohalogenation. Hydrohalogenation only has 2 steps: 1, 2. So 3 steps. We have what's called a slow step, and the slow step is typically the step where the alkene attacks. Okay, this is typically fast, where the nucleophile now attacks. So slow step. In general chemistry, you might have known this as the RDS, the rate determining step. The slow step is determining ultimately how fast this reaction goes. If all the other 2 steps are fast, super fast, then it doesn't really impede the reaction. It's the bottleneck, the traffic jam is right here. Okay, this is what's really determining the rate of reaction. All right. So we have 3 steps. If you think about your energy diagram, we have energy, and arbitrarily let's put the reactants here. The thing is, we have 2 intermediates before we get to the product. So we have actually 2 valleys. Since this is a slow step, we have to make that hill pretty high. Okay, and we'll put the intermediate now also right there. That's the carbocation intermediate right here. The other 2 steps are pretty fast, and ultimately we are going to make a product that's lower in energy. So smaller hill, go a little bit lower, smaller hill, or small hill, go low. You don't have to predict the relative sizes of the other, well, you do have to know that they're smaller. So just because we know the first step is rate determining, this distance right here, this activation energy, has to be bigger than the other 2. Okay. We're not going to make a distinction between the height of these 2 hills. Okay, they just have to be smaller than this hill. All right. We should assume that the product is lower in energy, so ultimately we have this line here. Okay, so the energy diagrams are going to look a little bit different from person to person. What I'm really looking for is that you have 2 hills. So not 2 hills. Sorry, you have 3 hills, right? Because we have 3 steps. The first step, the second step, the third step. Okay, so that's 3 hills, right? And there's 1 hill there, and 1 hill here. Okay. But the other features of the energy diagram are not that important. Like, I don't really care if this hill stops here or the hill went up to here, as long as it's smaller than this one. I actually don't really care if the intermediates are, if this intermediate is lower and this intermediate is higher. Okay, we don't have that information, or I'm not giving you that information to decide the stability of these 2 intermediates together, or versus each other. These valleys are the intermediates, I. These top of the hills are called transition states, and sometimes there's an asterisk. Actually, transition state, I think it's a double dagger usually, like this. Double dagger. There are 3 transition states. Okay. I am not going over how the transition state looks in any of these videos. That's one of the things that I am eliminating from this unit. Okay. So if you see anything about transition states in your problems, hopefully I would have told you to skip that, but you can skip it. Okay. Want to practice? Let's practice this one. Another alkene. I'm going to give you what I typically see for acid catalyzed hydration, H2SO4. That's actually one of the more popular reagents. Again, a little flexibility in organic chemistry, because one person might like to use sulfuric acid, one person might want to use phosphoric acid, one person may use either those 2, but understand that the effective acid is H0+. Okay, you're going to have to be able to recognize, be able to diagnose, these, I don't know, we can call them symptoms. They could be slightly different visually, but they all are leading to the same prognosis, or the same condition. Draw the product with stereochemistry when appropriate. And go ahead and press pause and see if you can match my answer. Okay, the answer is this. I can tell that from the very start that we're not going to make a carbon, so I'm going to draw this in my answer, not on a scratch sheet of paper. There's no carbon. Don't use wedges and dashes. I followed the more carbon cost rule. Why hydration? Why is it called hydration? It's because you're literally adding water, but water in a separated form. Here's your OH, and see, this carbon has 1 hydrogen, now it has 2. So I added water. Okay. And in the mechanism I actually did add water, it's just that this hydrogen is ultimately removed. Okay. You're making a class of molecules called alcohols, which is also good to know, because what if I have an alkene and I want you to make an alcohol? Okay, you have to know the reagents, but also later on, much later on, probably in exam 3, we're going to learn about synthesis. And I may just say, give you no hints, and I say make this from any organic molecule. Well, what's going to go in your head? I can make an alcohol with an alkene using acid catalyzed hydration. Okay. Do you see how the terminology is going to help me organize my thoughts? I can make an alcohol from an alkene doing acid catalyzed hydration. Okay. That is reaction 5B. Before I end this video, I have maybe 15 minutes of something I do want to discuss concerning reactions that produce a carbocation. So I'm not going on to reaction 5C in this video. I gotta give you a couple of side notes, and they're not, they're side notes, but they're so important, which is carbocations can undergo rearrangement. Our first two reactions produce a carbocation. We need to know, or we need to recall, carbocation stability. Tertiary is more stable than secondary, more stable than primary. Some of you are familiar or remember that we talked about allylic. At this point, we're not going to worry about allylic carbocations. Okay, let's just worry about the tertiary, secondary, and primary. So this is going to be tricky, because the example I'm going to give, oh, by the way, why don't we list? We get, or we produce in the mechanism, carbocations in what? In reaction 5A and 5B. Okay. If you study your notes regularly, you'll know what 5A and 5B is. I will never test what is the name of reaction 5L or 5D. Okay, you don't have to memorize that. But with this 5A, it's the first reaction we learned. Hopefully, by now, it's been, because you've seen this at least in 2 different videos. Whoops, almost messed up. 5A is hydrohalogenation. Spelling it totally wrong. And 5B is acid catalyzed hydration. Acid cat hydration. We know that both, right, both follow Markovnikov. And go through a carbocation. I'm trying to think if these are the only 2 that go through a carbocation in this unit. And I believe I can say that. Okay. Let me give you an example, because this is a warning. That carbocations can do something unexpected. Here's the unexpected thing that they could do. Okay, let's go back and let's try HBr. Let me draw you the answer. Let me draw what, as a student, what I would have done. I'm marking the 2 carbons that should get something. Remember, both carbons get something, except in this case, because the product is this. And it's going to look, if you're following, it's going to look very strange. What? I thought I had to add the bromine on one of these 2 carbons. Okay, according to Markovnikov's rule, you would predict the bromine would go here. Right? What is that? It looks like I made a mistake. It looks like I put the bromine here, which is not part of the carbon-carbon double bond. That's because a rearrangement happened. Okay. So what you were expecting for most of you, which is fine, because I haven't yet gotten over this weird behavior, you were expecting this, something like this. Okay. And if you do that on a scratch sheet of paper, you would also hopefully have realized that you created a chiral carbon. But that's not what's happening. So this is your answer, and your only answer. When something unusual happens, you want to go through the mechanism to try to explain why. Because right now, this is unusual. This is unusual. You would expect the bromine to be again on this carbon here. Okay, when in doubt, if you don't see the full picture, try to get at least the first step, and maybe things will start to fall into place. I don't know if we do the first step like we've been doing it, if we're going to get close to the product. But I know that typically the slow step in an alkene addition reaction is a pi bond grabs the electrophile. And we have this. For Kavli-Cox rule, the rich get richer. The hydrogen goes on the N carbon. The carbocation goes on this carbon here. And normally that's where the bromine would go. For my class, I am going to insist that you draw every product at each step. So am I asking you to draw bromine minus every step? No. Only when it was produced. It was produced in this step because we kicked out bromine. Okay. Normally the bromine would come in, but something odd happens. Or something at first unexpected happens. You have this hydrogen, and it's a little crowded, but I'm going to draw it here. That hydrogen is going to jump. Why it's going to jump? Okay. Now, you could draw this to the plus, or you could draw this to the atom. Okay. I really want to draw it to the atom, but the plus charge is in the way. But this tells me that the H is jumping one bond over. This is still a part of a reaction. This is still a mechanism. It's not resonance, okay, because an atom is moving. But can you draw me the result of this movement? Remember, before you pause the video, remember conservation of charge. If your net reactants have a charge, then your products have to charge. Just another warning. Since I'm not using the bromine was produced in the first step, but in the second step, I'm not using bromine. So what I'm expecting here is a molecule that still has a plus charge. Technically, you carry the bromine over, and yeah, you'll still have charge conservation, but understanding that the bromine is not part of the second step, your charge conservation task is to make sure that your product is net positive, positive 1. Draw the reaction, or draw the result, pause the video. Okay, when that hydrogen jumps to the carbon next door, that carbon next door is now neutral. It has 4 bonds. This carbon here is naked. That's where your plus charge is. The last step is, okay, we are going to take the bromine that we kicked out. Yep, and I'm going to put it over the arrow. It's a little bit of a stylistic point. When I add a molecule, well, this could have been over the arrow also. What I'm saying here is that, see, since this is not a product of the directly previous step, I didn't create bromine at this step. I'm actually bringing it from another part of the flask, and I'm putting it over the arrow. Because what I'm worried about, or what looks to me strange, is if you put here plus Br minus right here, plus Br minus, that kind of implies that you made that Br minus in the previous step. By putting it over the arrow, I'm avoiding that confusion and not putting in the Br minus plus here. Okay, a little bit of stylistic point. Will I take off points for putting the Br right here? I wouldn't, but I think it's just more elegant to realize that, yes, this Br is being used, but it wasn't created in the previous step. Now, here, right, you see how in this, our first mechanism of the video, the chlorine was produced in the previous step. So do you notice that the chlorine is not above the arrow? The chlorine was part of the result. And then I could just conveniently use that chlorine to attack. Not here. Anyway, this is your product. So let me describe what happened, because you're going to have to recognize that a rearrangement can happen. The rearrangement here is called a 1,2 hydride shift. Do you see how I didn't say proton? I didn't say hydrogen? Because a proton would have just given me the nucleus. A proton is transferred in acid-base reactions. Here I'm transferring also the two electrons. A hydride, as you recall, is this. Now I don't see that here literally, but literally I am transferring the nucleus of hydrogen and 2 electrons, these 2 electrons. That's a hydride shift. Why do I do hydride shift? and not in the other cases. Because what I need to have realized is that when I look at this molecule, and I formed the carbocation here initially, okay, I knew that because of my analysis, right? I should also see that it's next to a carbon that's tertiary. Okay, that's not always going to be the case, but in this case, yes. And by moving one hydrogen over, I could convert a secondary carbocation into a more stable tertiary carbocation. Spelling. Carbocation. Okay. Now there are rules that I am going to enforce because, heck, don't I have a tertiary carbon here? How come I didn't do a rearrangement in this case? The I went here. The I didn't go here after a rearrangement. It's because if you think about it, we start with a tertiary carbon, tertiary carbocation when we do the mechanism. You're not going to change the tertiary carbocation into another tertiary carbocation. So the rules here that you'll need to practice is that, and these are my rules. Some professors will say that anything is possible. You could start shifting hydrogens and other groups, but not only that, you could do multiple shifts, and you could keep shifting until you find a tertiary carbon. That opens up Pandora's box. So I'm going to say here, your shifts, or you could have shifts that create a tertiary carbon from a secondary carbon. I'm trying to visualize whether you could do that if it's a primary carbon. Yeah, it's possible. So you could have shifts if you're converting a secondary carbocation into a tertiary, or if you're converting, in very rare cases actually, a primary into a secondary or tertiary. I think the rule that's going to help us avoid this Pandora's box of having to move carbocations multiple times is you only do this once. You only get one shift. And that's good because now you don't have to worry about, do I have to keep shifting? Do I do a second shift? Do I do a third shift? So only do one shift. Okay. So I'm not going to shift the carbocation more, and it actually doesn't make any sense because this is the only tertiary carbon anyway. The last thing is that you could only do what's called a 1-2 shift. A 1-2 shift is just shifting a group next to its neighbor and have the carbocation jump and replace the spot. So it's a 1-2 relationship. They're next to each other. Okay, that's it. Oh shoot, this is actually really important. For my class, you only worry about a hydride shift, or, which we didn't see here, methyl shift. It's lowercase. So methyl shift is if you have a methyl group jump. Let me show you that example. Okay, let me show you a methyl shift. I am spending some time, right, on these carbocation rearrangements, and the only two that you have to worry about are hydride shift and methyl shifts. Even though I'm spending some time, don't go berserk trying to look for one. If there is no possible shift, then most likely there is none, right? There is no beneficial shift. Okay. Let me show you another example. That. And because these rearrangements or these shifts can happen with carbocations, what's the other reaction that we know produces carbocations in the mechanism? It doesn't matter if I have water on top or water on the bottom, H3O plus on the top or bottom. It actually doesn't even matter if I have H3O plus over here. Okay. I would put water actually under or over the arrow because that's acting more like a solvent. The product here, and I'll show you how I get this in just a bit. Ugh, very, very interesting. What happened there? Yikes. Not only did it not, well, I did put the OH on this carbon right here ultimately, but this is not a typo. There's another methyl group here. What? And also here we have 3 methyl groups on this carbon that I'm pointing at. That only has 2 methyl groups. This is your product. On a scratch sheet of paper, okay, this is where I'm going to separate the A's from the B's, it looks like. You'll notice that this is chiral. Okay. And in actuality, your answer with stereochemistry would look like this. Enantiomers, 50-50. Racemic. Because look at my pink asterisk. That is a chiral carbon that we did create. Okay, mechanism. Okay, pause the video and draw me the first step, the mechanism errors and the result. Okay, we're back. Mechanism error. Doop, doop. Pause the video if you need to copy this. How's that? So I said previously that if you have an opportunity to get the carbocation on a tertiary carbon, and you still have to follow these rules, only do 1 shift. These are the possible cases where you go from secondary to tertiary or primary to secondary or tertiary. Only do 1 shift, only do a neighboring shift, or what's called a 1-2 shift, and only shift a hydride or methyl. The thing is, I don't have any tertiary carbons, but I have this quaternary carbon that if I shift one of the methyl groups over, I followed my 4 bullet points on the previous page and I got this now. By shifting that methyl group over, this carbon right here is positive. No, it's neutral. Neutral. It's a little bit tricky because it's symmetrical, but see this carbon right here, the one from the end? I'm going to make sure that it's this carbon, and I shifted this methyl group over. So maybe I'll mark it with a dot. Okay, that's a CH3 group. The CH3 group now I would say is over here. The carbon that's naked is this one right here. Carbon that's naked is that one. This is called a methyl shift. Okay. And what happened? I went from a secondary to a tertiary. That is valid. I only do 1 methyl shift. I only do 1 shift period. And then now we're back to our mechanism of hydration. Same thing that we've done previously. So I do realize that, let me just finish this. Okay. I do realize that when I drew the product, the OH is on this carbon. But since the carbocation was symmetrical, it didn't matter which OH, because I'm getting the same product anyway. It's just that I rotated my initial answer. So here's your water. Again, remember that we added water, so you have to bring in both hydrogens. Again, you'll develop your own style and how you want to snake this mechanism around. But I ultimately have this product here, and you decide whether this product, okay, is the same as this product up here, and it is. Same connections. And now you could realize that you made a cut. You guys didn't stop me. Perfect. I hope some of you realize that this was a big mistake, which is great because it's a habit that I got to work on, especially before the exam. That's not racemic. That's not a chiral carbon. What am I doing? So, minus 2 points. Okay. The real answer is I get rid of this asterisk, and this is the real answer. When did I realize that? I realized that when I was staring at my final product here. That is not a chiral carbon. This is not racemic. So now everything is correct on this page. Okay. Do you notice that I like to use whiteout, but if I know I make an error over and over again, or it's a bad error, I'm gonna pay my penalty, and I'm going to show myself, or I'm going to remind myself over and over again when I study these notes that don't make this mistake. Okay, I was so eager to show you racemic mixtures that I saw a chiral carbon that didn't exist. Okay. But the methyl shift is proper, okay, and the products now are correct. If you're worried about shifting, I think for most of my classes, I will give a hint, okay, that there is a possible, okay, I'm not guaranteeing it, a possible carbocation rearrangement. But those of you who are understanding this point is you can recognize that just by understanding that if the carbocation goes here, do I have an opportunity to do a hydride shift or methyl shift to get a tertiary carbon? So this is the last thing I'll say. When looking at this starting material, without having to go through the mechanism, is what, because I'm not going to ask you for the mechanism for every single problem. I may just ask you to draw the final product. Say something like this. If H goes here, the rich get richer, and the plus charge goes here for the intermediate. Is there an opportunity to shift hydride or methyl to go from, this is a secondary, this would have been a secondary carbocation if I go ahead and proceed to put an H here and this carbon is naked. So to go from a secondary to a tertiary carbocation. Okay. That's where I'll end this video. I know we only went over 2 reactions, but these were important, and the things that we've learned in these 2 reactions are now applicable for the other reactions, and I'm going to go a little bit faster. Okay. For instance, you'll need to know what Markov means. You need to know what a shift means. You'll need to know how to draw mechanisms. You need to know what it's a slow step. You need to know when to draw all the lone pairs and when it's okay not to draw any lone pairs. Alright, so we've done all of that in this video. In the next couple of videos, we're going to go a little bit faster now that we know those concepts.